Good morning. My name is Paul Schwartz. I'm the co-founder and CEO of ThermoLift. I'm talking to you here outside of the McLaren engineering facility in Livonia, Michigan. McLaren is a wholly owned subsidiary of Linamar Corporation, who's been our partner in developing the Generation 3 ThermoLift heat pump. So we want to take you inside, show you two Generation 3 prototypes in the test stand, show you their performance, give you a little bit of background about how we got here today. Look forward to sharing this with you. Come along. So Linamar is a $6 billion global manufacturing company supplying the automotive community with machine components, castings, forgings, advanced manufacturing techniques for highly reliable and durable products, which will help ThermoLift transition from prototyping towards commercial production. So we're in the build room. We brought you here because we wanted to give you an idea of the different levels and design characteristics of some critical components that go into the ThermoLift machine, and also give you an understanding of the limited number of components in our device. Here we have our little buddy, the ThermoLift 3D prototype. It can give you an idea about the two moving components, the top displacer and the cold displacer. We have a burner head, the heat envelope that feeds energy into the device. We have heat exchangers, regenerators, and electronic controls that make up a ThermoLift unit. Laid out around us, we see all the components that go into the manufacture of a Generation 3 prototype, and we're going to go through them one by one. Professor, one of the biggest areas of concern we've had from the beginning of our program is cost. What are we doing on cost reduction, and your experience at Volkswagen that can contribute to the success of the company?
Yeah, we have already demonstrated the performance of our machine. Our next step is now to reduce the cost. This is a normal procedure in development.
So through Professor's leadership, one of the first components that we brought to Linamar was one of the most critical components of the machine, which is the hot heater head design. And it was this dome design that allowed us to avoid the use of very expensive Inconel materials, to use traditional stainless steel, which is a low-cost, easily available product standard for just about any manufacturing environment on a global basis.
Usually in Stirling engine this is brazed, but brazing is not a mass production procedure. You cannot put a piece in for 4 hours in an oven. So we did a lot of thermodynamic analysis, and we found that we can reduce the temperature of the tubes to 500 centigrade, then we can use stainless steel and don't need Inconel. And we are working very hard to laser weld these tubes to the dome. This could be done in some minutes, and it would fit in a mass production procedure. Yeah, this is another important and expensive part in our machine. And you see, we came up with the idea to replace fins with folded fins, which we can very cost-effective manufacture.
So Professor, as you may know, is world famous in his combustion system inventions, and we're porting now vast improvement in combustion system technology for an ultra low NOx or almost NOx-free emissions burner that'll be integrated into our machine as a proprietary technology for powering the ThermoLift thermally driven heat pump system. Springs are a critical component in this machine. We started with very expensive, ideally designed machine springs. The spring in my hand costs somewhere between $3,000 and $4,000 in prototyping form. We can reduce the cost of close to a $4,000 part to a $4 traditional wire spring in an assembly, which has eliminated side forces and in being demonstrated in the Gen 3 prototype to perform identically to a $4,000 product. And other areas of cost reduction can include optimization of our coils for our electronic controls, and stamping and or forging for production of our displacers. All this relates to production techniques that go down to material cost, high volume manufacturing for 50 unit a day production to 500 unit a day production, which is 1,000 units per month to 10,000 units per month, or 120,000 units a year. So the final two assemblies are the external skeleton of the machine, which consists of the hot dome and the hot end of the machine, as well as the cold dome and the cold end of the machine. And when coupled together at this joint, the top fits on the bottom, the internal components fit in that sleeve, and we go into mass production. We're working with one other group that we should, of note, on the cold end components. This steel housing should be replaced in the future with a composite prototype, and that composite is being developed by the Composite Research Center on Long Island. We expect to have that integrated into our Gen 3 machine in the next 2 months. Let's go on inside and we can meet our Gen 3 prototypes and part of the ThermoLift team. Here's some of our team: Ted, Nick, Christos, Adrian Tassinian, Chief Technology Officer, David Yates, Chief Designer, Jonathan Haas, Senior Vice President. We're going to go into the test cell and meet 2 other friends of ours. So let me introduce you to 2 ThermoLift Generation 3 machines in the test cell. We're operating a machine spring version here. We're operating a compression spring version here. So this is more of a raw prototype, and this is more of a production prototype, both operating side by side, performing virtually identically.
We made a test last week, and we ran the machines, and we got, it's a cold chamber which is underneath here. We got a temperature of minus 101 degree Fahrenheit. So it shows the potential of these machines. Of course, we will not do this in real life, but we can very nicely cool with natural gas by burning natural gas in the heater head.
So hello, my name is Christos Demosthenos. I'm the Senior Mechatronics and Control Design Engineer for ThermoLift, and my job right here is to create the control system for the heat pump that we're creating. Right now you will see basically this is the brains of the system, and all this is controlling all the different parts of the machine. We're talking about the motion control, we're talking about the burner control, and all the surrounding systems. All of these systems, they have to come together, and that integration is happening in this part of the system. Everything ends up right here in just one screen where we only have to start and stop the machine. So
I have the honor to do this easy job. So I start now the machine.
And the machine is running.
Now we are at 500. We are still at 1.7 COP. This is the energy what we are getting out from the machine. It's about 8 kilowatt from the hot heat exchanger, and about 3.7 kilowatt from the cold heat exchanger. Okay, now we are running the system at partial load. We have still a reasonable COP, and you see now we let the cold displacer not go at the same time when the hot displacer reaches the top center. By the way, this shows that we are hovering the displacer, so the displacer are not touching the dome, and therefore we have a very quiet machine. So by reducing the heat flow from the environment to the machine, we could show now a temperature of minus 101 Fahrenheit. I think this is quite impressive.
Moving over to the mechatronics, which is really the heart of the machine, instead of having that fixed 90-degree sinusoidal motion, we went to a mechatronic system where we drive the machine electromagnetically, and this gives us a lot more flexibility on the kind of motion we use in the machine.
I'm the Chief Design Engineer at ThermoLift, and the team behind me conducts all the design. We take our brainstorming concept ideas through to manufacturable components, with further studies to ensure that simulation and strength and thermodynamic capability is perfect. And then we also move the ideas from there to a more production viable, inexpensive component.
We're back at the Energy Center at Stony Brook University. The next 24 months are very exciting for ThermoLift. We'll be producing 20 prototypes. Those 20 prototypes will go into field demonstrations. Those will be at military installations. Those will be around the world at utility companies. Those will be at national laboratories around the United States to continue the evolution and cycle development of ThermoLift. The success of that will bring us to the next 200 units of production that will go into the field, to actual installations and begin sales as we move ourselves forward towards 50 units a day to 500 units a day, 10,000, 12,000 units a year to 120,000 or more. We look forward to sharing more successes with you in the future and getting back to you with more updates. Thanks again.